Good morning, and welcome to the sixth and final webinar of the Utah Connected webinar series. My name is Muriel Sochmil, and I will be your facilitator for this event. This webinar series, as many of you know, since you've attended several of our webinars so far, is intended to foster collaboration and promote information sharing among UDOT and its partners. It highlights 6 successful deployments across Utah, including significant deployments with connected vehicles that have helped to improve mobility, safety, and quality of life here in Utah. This webinar is being recorded and will be made available to the public within 1 week of today. Before we get started, I would note that UDOT does not explicitly endorse any one company, service, or product, but very much values its partners on these deployments we're highlighting through the webinar series. To get things kicked off, we first want to ask each of you who've attended with us today to answer a few questions. Your responses will be kept anonymous and combined with all other responses. This helps to give us an idea of who's joining us today. I'm going to give each one of you a minute to respond. The first question, what role best describes you? Are you an engineer, a planner, a researcher, consultant, policymaker, something else? What industry sector do you work in? The public sector, private sector, nonprofit, academia, or maybe something else? And then how long have you worked in the field? Less than 5 years, 6 to 10 years, 11 to 15 years, 16 to 20 years, 21 to 25 years, or maybe even longer than that. Perfect. So it looks like the majority of folks joining us today are engineers. You're in good company. We've got several engineers that are presenting today. Some of you are planners, researchers, other types of consultants. We even have one policymaker and a few folks joining us from other fields. In terms of the sector, we have a pretty good balanced mix of public and private and academics. For how long you all have worked in the field, it looks like across the board, some are just starting out in the profession, some have been around for a long time. Either way, we welcome your attendance at today's webinar, and we'll go ahead and get right into it. So automated vehicle road readiness. UDOT deployed 2 automated vehicles to evaluate the compatibility of Utah roads with connected automated vehicle technologies, specifically lane keep assist, or LKA, and advanced driver assistance systems. Each vehicle was equipped with a full suite of automated driving sensors, such as advanced camera, lidar, radar, and positioning systems. The vehicles were driven on different roadway segments throughout the state to record data from the automated sensors. This webinar will highlight for you the study's findings, explaining how well Utah's roadways support these automated technologies and identify challenges and opportunities for other DOTs across the country to consider in future deployments. If you have any questions throughout today's webinar, please feel free to drop them right there in the chat. It's an icon, or the Q&A feature, which is the icon located at the bottom of your screen. We should have time to get to everyone's questions today, but if we do not, we will make sure to follow up with you after the fact and get your question answered. Today's program consists of 3 amazing speakers. We'll first kick things off with Blaine Leonard. Hopefully by now you all have gotten the opportunity to meet Blaine, but for those of you who have not, he is the Transportation Technology Manager at UDOT. In this role, he leads the planning and deployment of connected automated vehicle technology. Blaine has chaired the American Association of State Highway and Transportation Officials Connected Automated Vehicle Working Group and has led the SPAT Challenge Tactical Working Group. He is currently co-chair of the AASHTO Technology Subcommittee and the Society of Automotive Engineers Connected Transportation Interoperability Committee. Prior to joining UDOT in 2001, Blaine spent 20 years in the consulting engineering business. Blaine has a bachelor's and a master's of science degree in civil engineering from the University of Utah. Blaine?
Thank you, Muriel, and thank you everyone for joining us today. Let me make sure I can get my screen shared here. Appreciate everybody being here. When we started planning these webinars a year ago, we did a lot of work to figure out exactly what we would cover and how we would do it. It's hard to believe now that we're on our very last webinar. It's been a journey. It's been a little bit of work. We hope everybody has enjoyed participating in these. 3 of our webinars were focused specifically on connected vehicle deployments. And our most recent webinar was focused on distributed acoustic sensing, which is using fiber to sense what's going on along the roadway. Today, we shift gears a little bit more and look at whether our roads are ready for automated vehicles. First of all, before we get into the content, I would like to thank the Federal Highway Administration, both in their national grants team and the local FHWI office, who have supported us throughout our journey of these various innovative projects. These webinars are in fact brought to you through our ATC-MTD funding, and we appreciate them. Today's topic specifically wasn't part of our ATC-MTD grant, but it's related to some other automated vehicle work we did, and we felt like it was important to share this out and would be interesting to people. I want to thank Muriel and her team at X Factor, who have helped us plan and organize and execute all of these webinars. They've gone above and beyond and really done an awesome job. All of you were here because they did a great job of marketing these, and so we want to thank them. I also want to thank today's presenters, who, aside from me, are Peter from UDOT and Phil from VSI Labs. You'll hear a fair amount of detail from them. Finally, of course, I want to thank all of you who are with us today and who may watch this in the future. We appreciate all of you joining. That's why we did this, so that we could share this with everybody. Some of you may be joining just this one webinar. Others may have joined others. I'd be sort of interested to know if any of you out there have joined all 6 of them live. We'd have a prize for you. I don't know what that prize would be, but thank you all for joining us and participating with us. And thank you for the questions that you ask as we make these presentations. They help us and they help everybody else. And that's been really useful along the way. So as Muriel said, our goals of these webinars is really to promote information sharing, to share our lessons learned with the rest of you so you can repeat some of our successes without repeating some of our failures, and to foster collaboration among agencies and entities who are trying to push the envelope and do innovative technologies. We want to support and encourage all of you going out and doing some of the things that we've done so that we can advance transportation, safety, and mobility. Speaking of that, 2 of UDOT's primary goals are safety and mobility. And in our transportation technology group, we are very focused on those 2 specific goals. In addition, as we've talked in the past, we're also interested in finding a way to get full situational awareness of our corridors, find out what's going on in our roadway network so we can respond more effectively, and to prepare our roads for connected vehicle equipped production vehicles, and I will add automated vehicles as they come at us from the automakers. As I indicated, today's focus is really about automated vehicle technology. This really focuses on our strategic safety goals: 0 fatalities, 0 injuries, 0 crashes. We believe that these advanced driver assist systems, or ADAS, and automated vehicles will improve safety on our roads and reduce crashes and save lives. We want to know how to support the safe development of those systems and encourage them to be more successful. And we've undertaken a number of projects to try to accomplish that. We are not a developer of automated vehicle technology, right? As a state DOT, that's not our job. One of the things we've spent time thinking about is, what is our role, especially with automated vehicles? What should we be doing to make sure that those can be safely deployed? And today's effort really focuses on that. Automated vehicle road readiness is the title for today. And as it says, we want to know if our roads can support automated vehicle technology. There are some things we can do and some things that may be out of our control. And what are some of those things? So in this particular project, this project was born out of an original desire to get an automated vehicle to drive from Salt Lake City to our southern Utah border about 300 miles without human intervention. As we evaluated the prospect of that kind of a project and started thinking about why we were doing that and what we were trying to accomplish, we started to shift to something a little more practical to assess how well our roads would support an automated vehicle on that kind of a journey. As I indicated, we don't build automated vehicles, and we felt like a study of our infrastructure and how it can support these vehicles was something that fit well in our scope of work. Modern vehicles today, as you'll see later in the presentation, overwhelmingly use cameras to see our pavement markings. How visible and consistent are those pavement markings? It's interesting as we talk to people about automated vehicles, members of the public, people who live next door to you and I, they have a broad range of ideas and understanding about how these automated vehicles work. They ask me whether we've got cables buried in the road that are telling the car when it's in its lane and when it's not, or whether there's some kind of satellite system feeding it. And many of them are surprised to learn that a forward-facing camera in the car, in their car, is reading the paint stripes. And so that just sort of reinforces that we've got some more work to do with public outreach, but also we've got some more work to do as agencies to make sure our markings are good. There have been some national studies on infrastructure to support automated vehicles. Specifically, there have been some studies that look at pavement markings, paint stripes, but there really isn't a good industry consensus supported by the makers of these devices, these vehicles, as to what we as agencies should really be doing. Should our stripes be wider? Should they be brighter? Should they be a different style? Those are questions that are still a little bit out there. And so we decided to look at ours and see if we could get a sense for our pavement markings and how well they could support these systems. So those are our project goals: assess the capability of our infrastructure and look at how good our lane markings are. We wanted to use actual onboard systems to make that assessment, and VSI Labs brought that capability to us. As we look at the results of these studies, and there were 2 separate instances of studies covering many roads in Utah, we ask ourselves, what improvements do we need? What kinds of things should we revise in our standards and practices here at the DOT to make our pavement markings more conducive? During this study, we brought in VSI Labs, and they surveyed 1,600 miles of roads, essentially. And you see those here on the map of Utah. Some of these are urban interstates in and around Salt Lake and in Utah County and in the city of St. George. Many of these roads are rural interstates passing through very unpopulated, sometimes remote areas of our great state here. We also did rural highways. Some of our major rural thoroughfares, even though they're just one lane in each direction, pass through a number of cities and towns along the way in some of our more rural parts of the state. We wanted to see how these systems work there. And you'll see that there are differences between that rural road when it's passing through farmland and that rural road when it's passing through a town. We also looked at canyon roads, and you'll see a couple of those, Big and Little Cottonwood Canyon specifically, in the Salt Lake area that go up to our ski resorts to see what we could learn about those roads and the capability of these systems to operate there. We also did some daytime and nighttime studies to compare the capabilities with sunlight and without sunlight. And I believe Phil will talk about some of those. We considered trying to do some studies that compared clear weather with rainy weather. We weren't able to figure out how to turn the rain on when the study was going on. So that didn't really happen, although we would be very interested in that if we could figure out how to time that appropriately. So that's sort of a summary of why we did what we did. We're going to get a good detail today from Peter from UDOT and Phil from VSI about what we did in this study and how it works, how the systems work, and what the results were. For a good succinct summary of what they're going to talk about, if you go to our website, transportationtechnology.utah.gov, where we will also post the video of today's webinar and all of these presentations. If you go to that website, you will find there a YouTube video that's a brief, succinct summary of this project that was done a year or so ago. And we will now introduce you to the project by showing you that video, and then we'll move on to Peter and Phil. So with that, I'll turn it back over to Muriel's team, who will play this road readiness video. Thanks for being with us today.
Connected and automated vehicle technology is the next opportunity for a significant leap forward in both traffic safety and mobility.
One of the key goals we have here at UDOT is safety. We want to arrive at zero fatalities, zero crashes, zero injuries. We believe that connected and automated vehicle technologies will help us get there. We don't know how well they're going to work until we try them. And we don't know how ready we are for some of these technologies until we try them and do them. And this study gets us there.
In August 2021, UDOT partnered with VSI Labs to conduct an automated vehicle, or AV readiness study, to evaluate the compatibility of Utah roads with automated vehicle technology. The study was conducted by a team with 2 vehicles, each equipped with advanced camera, lidar, radar, and positioning systems, which are the technologies used for vehicle automation. These vehicles were driven on different roadway segments throughout the state to record data from these systems.
The goal of this project is to assess whether our roads are ready to support automated vehicles. We often ask developers of automated vehicles what they need from our infrastructure. And they say, well, you need better paint stripes, for instance. This study is going to help us get a little more specific about what features of our roads are helpful or not helpful for automated vehicles. If an automated vehicle is driving down our road, can it interpret what it sees effectively? Or do we need to be doing some things to get our roads ready? These vehicles see the stripes on the roads, and that's how they keep themselves on the road and in the lane.
Nearly half the cars sold have forward-facing cameras that are reading lane markings for their lane keep assist technologies.
As a part of the AV readiness study, VSI Labs surveyed over 1,000 miles of roadway within Utah over these 3 routes.
We picked 3 very different corridors. First of all, we started with Interstate 15, and they drove from St. George to Salt Lake and then back to St. George, so we get both sides. Then we picked a more rural but major corridor, US 89, from Salina to Spanish Fork and back. And then we decided to try Little Cottonwood Canyon.
We are able to take the data that we collect on these missions, we bring it back to our lab, and we perform what we call post-processing. At the end of the day, we're able to find areas where safe operation of automated vehicle technology isn't safe.
The data collected from this project indicated that the majority of the surveyed roads are very suitable for lane keep assistance and automated driving systems. The study identified a few elements of the surveyed roads that need improving, such as restriping occasional faded or missing lane markers, adding on-ramp and off-ramp blend area striping, covering up ghost marking or lane scars, and utilizing high-contrast lane markers.
This allows us to start planning our maintenance operations in UDOT to say, here are the standards we need to meet with our pavement stripings, for instance. Here are the problems we need to fix. Here are the issues we need to solve.
To further Utah's vision of connected and automated technology in our state, UDOT will continue to research and gather data to improve AV readiness. Studies such as this will help UDOT to develop technologies that will move us significantly toward our vision of zero fatalities, improve mobility and access, and bring quality of life and economic enhancements.
Perfect. Hopefully that video helped to explain the deployment that we'll be talking about today. We dropped 2 links in the chat. The first link goes directly to the UDOT Transportation Technology website, and the second link is to that video. I'm now going to introduce our next 2 presenters, Peter Jager and Phil. So Peter is a project manager in the Transportation Technology Group at the Utah Department of Transportation. Peter leads the deployment of vehicle-to-infrastructure (VTI) systems. He has more than 20 years of experience in the traffic engineering field, both in the public and private sectors. Peter has a Bachelor of Science degree in Civil and Environmental Engineering from the University of Utah. He is currently serving as Vice President of the Institute of Transportation Engineers Utah chapter. Phil Magney is the founder and president of VSI Labs. Phil and his team conduct applied research to examine the performance and functionality of active, safety, and automated driving technologies. VSI performs functional examinations of HWSW components, including sensors, high-definition maps, machine vision, INS and GNSS, neural networks, connected services, and accelerated computing. Phil is trained in ISO 26262 and has practiced functional safety within the context of active safety and automated driving applications. He has a deep understanding of automotive electronic systems, including active safety, connected vehicle, and automated driving technologies. He is actually the author, he literally has written the book, of numerous reports and papers for industry trade publications, as well as being a frequent speaker at global automotive conferences and symposiums. Phil is a graduate from the University of Minnesota, where he studied math, information systems, and economics. So a numbers guy. In 2019, he was appointed co-chair of Minnesota's Council on Connected and Automated Vehicles. Phil is currently an active member of SAE International and contributor to ITS International. So with that, we will kick it to Peter first and then Phil.
Load up the presentation and first off, let's start talking about levels of driving automation. Vehicles vary between level 0 to level 5. These are the levels that the Society of Automotive Engineering, or SAE, has set out to describe different levels of automation in vehicles today. So level 0 would be no automation for vehicles as they started that require 100% operation by a human. Features such as cruise control start at level 1 that can maintain the speed of a vehicle on the roadway. You can take your foot off the gas, but there's no other operations. And level 2 is where we are at today, where we have partial automation, where a vehicle can keep itself in the lane, sometimes can monitor its speed with adaptive cruise control, keep it within range of the car in front of it automatically, but still requires hands-on and on the wheel, eyes on the road, and operation by a human. So what auto manufacturers are aiming for is levels 3, 4, and 5. Level 5 not being present today. being able to operate under any conditions, anytime with full automation. But 3 and 4 are starting to see on the horizon here, what we're studying, where there is some partial automation and robo-taxis that are starting to exist. And in some cities, we have Cruise, we have Waymo, where you can hail an automated vehicle that comes up and picks, drive you somewhere within a limited area, but with no human behind the wheel. It can fully drive by itself under certain conditions and within a certain operational domain. So here, what we're looking at the state is to see how these vehicles will operate on the roadways today. So our primary goal here, as Blaine mentioned, is safety, 0 fatalities. UDOT is focused on improving safety for all users of the road network as well. The 0 fatalities doesn't just apply to vehicle crashes, but to protecting all users, from pedestrians to cyclists to transit users. So we need to know how vehicles will operate, not just the ones people are driving, but automated vehicles will operate. And even today, most new cars are sold with these technologies such as lane keeping assist, automatic braking, and adaptive cruise control. And here's more description of these technologies. So even though level 5 is far out in the future, these technologies are here now. These are on the road today. Lane departure warning. Warning system that'll warn you when your car's drifting off the road, whereas lane keeping assist will actually nudge you back into the lane, kind of like having bumpers on the side of the road to keep your vehicle in the lane. And active lane keeping or lane centering actually puts your car in the middle of the road, keeps you driving down the center, kind of like being on rails. So these are level 2 automation features, or level 3 even, level 2 plus, some would call it, where you have full lateral and longitudinal control. They're appropriate for use on a highway. So here's a quick look at the percentage. When we say these features are available today, they're in pretty high percentages on new cars that are being sold today. The ones you see circled there, lane departure warning is in 70% of new cars and soon to be 95%, so almost ubiquitous. Lane keeping assist, slightly less at 60 and 85%, but these are not just desired features, but common in new cars today. So as older cars go off the road and replaced by newer cars, it's going to be very common to have these in nearly every vehicle on the roadway. And here's a quick look. If you download the presentation later or look at it on YouTube, you can get a look at all these acronyms. There's so many in the automotive world, but here's a good look at all the technology mentioned on the previous slide, good description of it. So I'm going to kick it over to Phil here, talk about how do cars read the road. He's going to talk more about the technology that was used in the study, and then show some of the data samples that were collected across the state as part of these studies.
Thank you, Peter, and welcome everyone. And thank you, Blaine and Muriel, for setting up this opportunity for VSI to share some of the findings. Yeah, so we were really fortunate to get this opportunity to do this study. Now it's been a couple years ago when we started it, and then we did a second iteration last fall. And it's really given us a tremendous insight into essentially how these vehicles read the road, how they react to certain situations, and general characteristics of vision systems. All right. It appears as though the deck has stopped. Bear with me.
So let's have you stop sharing for a minute and reshare and see if that works.
Thank you. Here we go. All right, back on track. Thank you. Sorry about that. So let me begin by telling you a little bit about VSI Labs. Like UDOT, we are not in the business of building a better self-driving car or a better ADAS solution.
or a better algorithm, but rather we're in business to help those that are on this mission to ultimately deploy, connected and automated vehicle technologies, as well as all the ADAS systems that are coming into the market now. And we can safely say that really these ADAS systems are really the building blocks of automated driving. Well, as Peter mentioned earlier, a level 1 system, whether it be ACC, that's longitudinal control, LKA, that's lateral control. So, 1 + 1 = 2, literally. So that's we're in the business to help those that are designing these systems, both on the industry side as well as on the infrastructure side, because that's half the equation. How do they read the road, and how do they react to scenarios and situations that they're going to encounter on a day-to-day basis. We've been in business about 8 years, as a matter of fact. With respect to the lab, we operate a lot of test and demonstration. We have these vehicles, so we're able to integrate different sensors into these vehicles and test them and demonstrate their performance, and really do functional validation of components largely. Our vehicles offer a shared platform, in a sense, for those in the ecosystem that want to see how their components work within the context of a full by-wire vehicle. So the sponsored build is how we are able to fund this research, and it gives us tremendous experience with components. And so part of that process, or another service that we provide, would be proof of concept testing. And these are going to be products that are not in the market, but those that are in a prototype stage. We've been doing a lot of work with different camera technologies, as well as thermal cameras as of late, and different IR systems. As you may have heard, the new NHTSA proposed rulemaking is going to really up the ante on pedestrian detection, as well, and VRU detection. And so, the new sensor technologies may have a bright future as a result of that. We do data collection. We utilize our vehicles, operate them on the road, and we record all the data. Recording the data is really vital, because that's where the analytics lie. It's one thing to operate a vehicle and make note of when it had a problem, but really to fully decompose that, you're going to have recorded data that you can, play back and re-examine. And in the case of the agencies, and in the case of AV Readiness, we're really collecting this data for purposes of evaluating how lane detectors and these lateral control systems read the road. So it's really the machine readability of the road that we're able to measure with this. Then we do functional validation of components. We do a lot of work at the proving grounds, using different types of VRU characters, soft pedestrian targets, for example, as shown in the picture on the right. So just a few opening remarks about lane markings. Really, when it comes to these technologies, they're the rails for automated driving systems. They really are the ultimate ground truth, and they do have the highest priority when it comes to applying technologies to determine where the car is going. So even if you have a highly automated vehicle with high definition maps, for example, and precision localization, and you're able to, operate even when you cannot see the lane markings, in a situation like this, your GNSS probably isn't going to be accurate enough to even make that work. So at the end of the day, you're always relying on the actual lane markings to give you that ultimate ground truth. Nowadays, it's important to point out that really most of your lane detectors are convolutional neural networks. So those are AI trained detectors. AI has really been making its way into automotive for about the past 5 or 8 years even. because it's really an excellent application, or AI is, for image classification. And the other characteristic with AI-based detection algorithms is that they can evolve and they can adapt. And you know, as new data is collected, those algorithms get retrained, they get smarter, they're able to handle different types of situations better, and those algorithms get pushed back out to the vehicles in the fleet. How do cars read the road? It's amazing what a camera can do, and what you can do with AI, and that's exactly what's happening here. In this example, we're actually seeing 3 different detectors operating simultaneously, and you can see where they all are important naturally for these applications. Obviously, you can see the lane markings. It's annotating that where it thinks the lane markings are. Okay, and it seems to be doing a pretty good job at that. I don't see any problem with that whatsoever. The greenish area is really examining what we call drivable free space. So that's like that's telling the vehicle that, look, this is here's the road, okay, that, and never mind lanes, but this is the road, and don't even think about going off the green. That's what we call free space detection. And then obviously it's classifying vehicles as they go by, and it's even doing a pretty good job even with the oncoming vehicles. So again, this is what the car is going through. Now, what happens when you're on a dirt road? Well, obviously there's no lane detectors, and so you can't rely on that. I'm not suggesting that this is safe or even necessary for dirt roads like this, but if you were to apply it to a situation like this, you would have no choice but to use a free space detector that's going to at least tell you the drivable free space, and then maybe your algorithm is going to tell you to kind of center itself between that. Without lane markings, you're not even going to really know where the lane is, or whether you should be the right or the left, or even what to do when you have an oncoming car. But the fact of the matter is, you can do a lot with cameras. When it works really well. And these things, it's amazing how advanced these algorithms have become, even in the last 2 years, since from the time we started this study. The algorithms are getting and the cameras are getting so much better too, especially at dealing with contrast and situations like that. Yeah, this is US Highway 2. This is up in northern Minnesota. It's operating on rails here. That rumble strip in the center doesn't hurt. In this case, it's not having any trouble finding the lane markings. But if those lane markings were a bit faded, having that rumble strip actually is going to enhance the detection. So we're going west with our survey in a couple months to do US 2 in Washington State. So we're looking forward to that. A perfect 10. It's a little pixelated here, but it doesn't really look like that way. But a perfect 10 is 99% KPI ratings. And like I said, when it works really well. This happens to be a section of I-94 that's recently been resurfaced and done so with CAV in mind. And so a lot of new materials were used and different applications and so forth. We have a whole segment on I-94 that we're going to be ready to release in the next week. So what is it? Okay. It's a survey to determine if automated features are safe on your roads. As I said, we're really out to measure the machine readability of these roads. And then in that, and then our goal is to call out areas where the driving systems could potentially fail. Likewise, we also call out areas that work really well, just so we can see what's going on there too. It's interesting. And then we call out other areas that may prevent safe operation, whether it's limited shoulder width, or maybe it's too tight of a curve, or maybe too much of a slope, and you can't see far enough ahead. So our goal is to really provide actionable insights that can be used to heighten the safe operation of these ADAS and automated driving features. So what messes things up? Well, limited, it's all about contrast at the end of the day. These detectors are looking for longitudinal patterns, okay? And it's interesting, we'll see in a minute, but they'll actually detect, seams and joints and things like that. Likewise, they can detect lane scars and rumble strips and surface material changes as well. But the contrast is key. And against concrete surfaces, for example, in wet surface conditions and so on. Lane spacing and gaps, especially in blend areas for ramps, that causes boundary conditions. That's probably the #1 complaint of people with these technologies, is that when you get in a wide blend area like that, the vehicle will start to wiggle. Worst case scenario, on an off ramp, it could inadvertently, take the off ramp. The geometry, as I said, slope can limit the look ahead range. Didn't really have too much of an issue in Utah with that, but except for the canyon roads, there we had some tight curvatures. False positives, that's another issue that we're measuring. You've probably heard of phantom braking and things like that. That sometimes is caused by some infrastructure. And usually it's permanent infrastructure, so there's not a whole lot you can do about it, other than the makers of the radar can use it to better filter, potentially false positives. And likewise, new lane markings that the algorithms are not yet trained on, that's key here. And this is the way these AI-based algorithms work. You train it with ground truth, so with all kinds of different variations of markings that it's going to see, and that is going to substantially improve the outcome. So yeah, we do it all with a camera. We also have a lidar, and we also have radar, but since all these applications rely exclusively on the camera, that's what we're focusing on, is what the camera sees. So that's the look ahead range. That's an analytic, that's a number, based on a given threshold. The stability of the lane detection, the confidence of the lane detection. Confidence is a number that the algorithm spits out, and when it falls beneath the confidence level, that's when the system is going to ask the driver to take over, or that your automated lane keeping is going to go away or be shut down. And then drivable free space. We measure the width of the road now, or the width of the lane, and I mean, most of the time we know what it's going to be, but it does vary. We operate these vehicles, they're loaded with technology, lidar, different kinds of lidar, different types of cameras, thermal camera, radar. We operate these vehicles. You can see the rack system, so we can constantly change things out or whatever. We also record from behind the windscreen too, because that's important. That's where most of the installations actually happen. So that's actually a better placement. Plus, it keeps the sensors dry. Because I tell you, when you're operating in a heavy storm, these sensors can't see anything, to be honest with you. And if it's ice, they're going to get coated and covered in no time. And so really the only thing that's going to work effectively is sensors behind the windscreen, or some other mount module that's got heating and cleaning elements in it. But for our purposes, we can collect high fidelity data with our setup. We can create a digital twin because the fidelity is so perfect with the full data set. We also operate a dashboard now. So our surveyor console, when we hit the road, we've got this console that are ready, to start recording, to tag what type of situation it is or what the weather's like. We can preview our cameras. We can see how much storage we have left. We can even monitor the temperature of the computer. So we're pretty proud of that. And then best practices. So we're running these in shadow mode, okay, and driving a perfect line, okay, because that's best practices for creating analytics. And then when we post process the data, we can call out all these anomalies. All the data is recorded with a lot of computer gear associated with that, and a lot of storage. The surveyor operates the console. Sometimes we'll have an engineer in the seat operating the console. It just, it just depends on how busy they are or what the situation is like. Driven at posted speeds. Again, best practices. If it's a multi-lane highway, we drive in the right lane unless overtaking. Okay, so this is going to expose us to all the ramps. Generally, if you're in the center lane or the left lane, you're not going to be able to pick up the ramps. So we drive a proper human line. The process starts with the collection. The survey itself is done. Okay, all the data then is uploaded to the cloud, and it's there that we can start to apply our different algorithms. And these are constantly changing and evolving at VSI. We're adding new tools and KPIs so that we're able to generate not only the visuals, but the analytics to go with it. And then ultimately we provide an output tool that allows the user to actually pull up each of these items, look at them for themselves, and literally go through frame by frame to see what's going on. We use 3 different detectors nowadays, but we run an Apollo lane detector, that's open source. We run a lane net detector, that's open source. We also run YOLO-P, which is our most efficient and highest performing algorithm. These are open source. There's a lot of open source tools, but it doesn't mean it's plug and play. There's a lot of parameters that have to be set up to make these work properly. And it starts with massive amounts of data. I would say in Utah, we probably had 6 or 10 terabytes of data in all. Ultimately getting that into actionable insights is the goal. So we run all kinds of algorithms on it, and post-processing of the recorded data, and then ultimately produces the output for the roadway segments, or the campaign, as we like to call it. Some things that we're able to common call outs, a lot of different things, as you can imagine, but a blend area gap or a camera dazzle effect, that's coming out of a tunnel or something. That's kind of an interest. Not a lot you can do about that, by the way, but a camera is generally blinded for a few seconds when it comes out from a tunnel or a big overpass. The cameras are getting better, though. They're able to adjust much faster. Anyway, going on, curvature situations, high contrast markings, we'll call those out when we find them because they're always interesting to look at. Ghost marking scars, the ramps, poor center line, poor contrast, depending on if it's a light surface or a polished surface or a wet surface, a general poor visibility, temporary markings, traffic jam scenarios, and the like. This is a common scenario that anybody that is, I think I mentioned earlier, driving with these technologies gets frustrated all the time. The one on the left, it can't help itself. It wants to center itself. And so when you get to this unmarked blend area, the vehicle will start to wiggle a bit. It can be mildly annoying, although not necessarily dangerous. You might say, well, why don't they just bias it to the left? Well, that would create other problems. So, but they're getting better at that. It's still there, though. On the right side, you may have a scenario. This is actually more can lead to a more serious situation, particularly on a bend like this. The vehicle could easily just go straight and then ultimately get caught in that off ramp and at speed. So, the obvious answer to that, is these dashed markings. I think they're probably equally beneficial to humans or to the machine. So we talked a lot about the route, and so I'm just going to skip that already. You got it loud and clear from Blaine earlier that we covered a lot of diversity in the road types, and so we were kind of covering all the different bases. General observations are as follows. The interstate performance was generally very good, except areas that have been recently resurfaced. It's pretty obvious there. Not calling out the ramps here. I guess that's the next bullet anyway. We did test I-70 in both day and night, but generally speaking, interstate performance is good for all these technologies. And furthermore, I would say, if there was ever a place to use this stuff, it's going to be on the interstate. So the technologies are going to be switched on in a good percentage of those vehicles. Ramps are probably the leading cause of confusion for camera ADAS systems, as I mentioned before in the previous slide. Performance on the rural highways is generally very good, probably better than expected, to be honest with you. And we've found this in some other states as well. But yeah, some of these federal roads and state roads are, even though they're 2-lane, they're highly suitable, and you can expect that the technologies would be used a lot on those types of roads. The canyon roads were very challenging, tight curves, vulnerable road users, or too much traffic problem. The off ramps are vulnerable, as I said. These are stills, obviously. A couple different examples. In the top example, you can see there is a faded dashed marker there. But the faded marker is not enough for the detector to have enough confidence to put a line there. So it is detecting the one to the far right, and that's going to lead you right into the ramp. And so that's obviously not a good scenario. I think that's the interstate. The one below it, I believe, was on one of the canyon roads. You have a right turn lane. Same type of thing can happen, where it's going to get confused, and it could easily find itself in the right lane when it doesn't want to be in the right lane. So that's why these dashed markings at ramps are so useful. This was in the video, of course. Normal detection. 5 frames later, miss detection. This is the ghost marking or previous marking that was still somewhat visible. Generally speaking, you can live with ghost markings as long as your main markings are strong and in good shape, because they'll take priority. You can get misdetection from tire marks, as I mentioned, or from expansion fillers, as I said earlier. It's looking for those longitudinal patterns, and it's going to build a line where it thinks there should be a line, okay? And so if you drive a Tesla or any LKA car, you'll probably notice the similar type of performance where it's able to attach to a seam. In the right case and the right picture, obviously that seam just happens to coincide with the where the lane marking should be. So that same with the tire mark on the left. So that ended up working out. Day and night performance. This is a very good stretch of road, particularly here. Detection is very solid, probably better in the day than at night. The retroreflectivity, I think, was pretty good, and so we didn't really have any issues. The only time we had an issue at night was when we were traveling through Utah in January. We were on I-70. It was snowing like crazy, and it was just with the headlamps, the human couldn't see anything, so the camera couldn't see anything either, and so it just nothing worked. State Highway 50, we've got a lot of experience on that road, and the systems work really well on that road. Yeah, really strong detection and good surface and everything else. We're even able to traverse a rural town to some extent. You can see when you get to an intersection, though, you have a momentary loss of detection, and so that's not good. So yeah, I mean, in this case, this very small town, in theory, you could easily maintain full lateral control and get through there probably, but I wouldn't recommend it, just because that's I don't think that's necessarily the safest place, especially when you have people. Glare is a problem. I mentioned this earlier too. Here you're getting polish, some glare, just a kind of a tough momentary misdetection. The cameras, like I said, are getting so much better, though, that you're able to compensate for that overexposure that you would get in that type of situation. Like this example, for example, our detectors is working quite well here because the markings are so strong, and so that's why I can cope with this. Even the glare situation. The only thing I would point out on this one is here again, you've got the right turn lane coming up. As we approach it, I believe right about now. And so, a dash line's probably better. See, now it's off to the far right. And so you're going to get some lane centering issues here, and then you encounter that line again. So the detectors are working fine here. It's just that that particular right turn lane ideally should be marked with a dashed marker. Similarly, if you have a left lane exit on a 2-lane road, you can see the detectors are working just fine. Very good visibility, very strong detection. But when you get to this left turn lane, I think it's coming up right about now. Yep, you see, it's totally confused, and so you have to, the vehicle would get way off center in that type of scenario. Apache services, that's kind of a no-brainer. You can see there's just really struggling to have enough data to work from here. And so you see there's just a lot of bouncing around and really low scores from a stability standpoint, especially in this patchy area. This, I guess, is not a video, it's a still, but you can see here again that your detector is, at this point, this one is starting to pull this way too. So this is a vulnerable area, particularly this one, because there is a slight bend in the road. And so the vehicle's natural sense is going to be to go straight, especially since the right lane is veering off to the right. So that's why the off ramps are more dangerous, in my opinion. Yeah, poor markings equal poor performance. This one is just really having a hard time. It's a section that I think is largely under construction now. I'm not sure, but at the end of the day, it's all about the markings. And if there's any compromise, things start to fall off, and that's particularly on that right lane. Missed detections. This is a real problem. As you can see here, you got so much going on. The right detection is okay here, but the left detection is actually okay here. But now you throw that patch in there, plus that scar, and it just, the detector just doesn't really know quite how to handle that. And when, like I said before, when it works well, it works really well, and most of the time it does. But there's a reason why these systems are only operable under human supervision, because they're not perfect. And if the markings are compromised in any way, the performance is gonna suffer. It's gonna turn itself off or tell the driver to take over. And the other thing I'd like to say too, yeah, it's these cameras, like I said, they're getting better all the time, but if you have a bad weather situation, and if the human can't see, there's a pretty good chance the camera can't see either. Your only hope, nor could lidar for that matter, okay? So just keeping that in mind. Some of the new IR sensors have a little bit more all-weather performance, but anyway, I guess we have some canyon road evaluations. As Blaine said, we did both big and little, and this one's a good example of a turning radius that's just simply too tight. So it's really messing up the system. It doesn't have a field of view that's wide enough to accurately read that road, and this is probably a 10-mile-an-hour corner. Of course, I wouldn't advise the use of it because these things don't work well at slow speeds anyway. But in this case, it wouldn't permit you to operate because it can't see enough of the right lane. Oops, yeah. When you have an area that's good, it's really good. Both of those canyon roads had fairly long stretches where things are just fine, and you can operate it without any issues at all. But sooner or later you're going to have some challenges. For example, this is a area that was recently resurfaced, obviously, and the right detector, since again looking for longitudinal patterns, is able to detect that road edge, or that seam, I guess you could say, where the new asphalt meets the old, and it's able to plot a line there. So it look for the next best thing and fit a lane or a line to where it thinks that lane edge is. In this example, of course, you have a vulnerable road user. You have new surface. There are no lines, but there is these tiny markers that are clearly placed where I think the painted surface is to be applied. Not applied yet, but you can see the detector actually is localizing off of that reasonably well. It bounces around a little bit between that and the road edge, but it gets the job done. Anyway, another situation where you start encountering this this type of lane scar, and it's really fighting to stay on the painted line, but sooner or later it gives in, and the detector starts to think that scar is the actual line. It's bouncing around a bit, so very unstable at this point. So key takeaways. I'd like to say I-70, for example, is ideal for automated driving systems. We have a lot of experience on I-70 because we did that both day and night. We also think that's a terrific segment that could be applied for a commercial route. There's not a ton of exits and ramps, and it gets twisty in one part, but it's not too bad. State Highway 50 was ideal for the automated driving systems. it's straight and void of towns, except for maybe one or two. We did 224 on the survey about a year ago, and that was fine. The markings were good, but you would require close supervision as you get close to those ski towns, again, because you have more cross traffic and more pedestrians and that sort of thing. Big Cottonwood Canyon, it's just too curvy, too many VRUs, as I said before. And of course, recent construction in certain areas was void of markings. And I-80 is also ideal for automated driving, except within the 215 loop, just because there's too much construction. And there's patchy surfaces and poor markings, just a typical, just too much going on in a construction zone to rely on these systems, in my opinion. I also will say I-15. We have a lot of experience in I-15 as well, and that's generally that's a very good chunk of interstate as well. High volume traffic and but very well marked. So I believe that's a wrap on the deck, and I think we can take some questions.
Perfect. I'd like to invite Blaine and Peter to come back with us as well. Phil, thank you so much for your presentation. We do have a number of questions. And a lot of them are in technical in nature, which we can expect given our subject matter today. So we'll jump right into it. The first question comes from an anonymous attendee. And this person asks that they recently saw an online debate of whether ALKS is a true level 3 feature or not. Given that the UN regulation 157 has detailed so much on ALKS, will the SAE amend J3016 further to reflect choices or levels on this feature in more detail? Like, what are your thoughts there?
Well, ALK is a function of level 3. I mean, ALK is lateral control, and lateral control on a level 3 system, for example, is going to probably rely on both lane markings. So it's going to have its vision systems. And then it's also going to most likely have a high definition map. So it's going to have virtual markings within the brain of the computer. And then the vehicle will really have a redundant method of positioning itself. And so I don't look at those. ALKA is also known as LKA. That's the problem. There's so many acronyms. There's LKA. LK, as USDOT defines it, lane keep assist, and as Peter said, is just a nudge. Automatic lane centering is the full lateral control. Anyway, as I said, it's a subset of level 3 performance, but level 3 performance is going to have more technology to help it out.
Okay. Blaine and Peter, do you have thoughts on this as well?
I do not. Bill covered it.
Okay, that sounds great. So we do have a question about cost, and I know this will be, highly variable and dependent on the deployment specifically that any DOT would undergo. But what are some, Blaine and Peter, best practices or principles that your peers across the country should consider when it comes to the costs associated with a deployment like this?
So we originally entered into an agreement with VSI Labs through what we call an experimental procurement to try something out, and paid them to come in and survey first about 1,000 miles of road, and then a second time through about 600 miles of road. And to be perfectly honest, I don't remember what we paid for that. And it's probably different than what someone else would. As Phil has described really well, the system they have developed has evolved significantly. And some of what was done in the first survey has been improved and automated a lot. And so there's a lot of capability there. So whatever we may have paid for it is probably not representative of what you'd pay for it today. But I saw, and I don't know if this is sort of one of the drivers for the question. I saw a question from Eva, a good friend of mine, who wondered about the ownership of the data, which is a great question. And I thought about that, and Phil can correct me if I'm wrong. I believe our contract says that UDOT owns the data that was collected. However, UDOT doesn't possess the data that was collected. After Phil's team collected all of this data, and there's a huge amount of it, as you saw in these videos, there's a lot of post-processing of the data, but he also collected lidar data from the lidar units on the car and other things. And we had a conversation about what to do with that data. And we didn't have a place to put it or a real use for the direct data. So what Phil has provided to us is a portal that we can log into and get access to that data in its processed form. So the videos that Phil showed, we can log in and view those videos on any of our roadways statewide, pull out still shots, look at the data, the way it was analyzed, and get full access to it. So we have that data available to us through a portal. We don't have to pay to continue to access that. It was part of our original contract with VSI. But that's a usual question we talk about is, what kind of data do we have? What are we going to do with it? Who owns it? How do we get to it? And this worked out really quite well for us for the uses we need. Peter's had a little more experience accessing some of this data that I have, but it's been useful. Now, Phil, have I misstated anything, or Peter?
No, I think you got it good. You covered it well, Blaine.
So the online tool they provided, the portal, we've got an online tool where you can step through frame by frame even. So there's a lot of value there you get from the data. He showed samples here. We got a report which showed, some still images of things. We could print it out as a report and find, highlighted areas. Oh, here's where we found the pavement patching or the reflective, the different highlights he talked about here. But we can go back to that and look at it frame by frame or show it to somebody, or there's a project going on in a certain segment. Say, oh, well, here's what we found there at this point in time. So yeah, there's a lot of value too, not just in the raw data, but in the portal and in the whole package.
Yeah, and our goal is to make it more efficient. We've actually mobilized it now. We can package it up in a Pelican case and get on an airplane and go to a destination and rent a vehicle and attach this ground truth rig to that vehicle and do our data. So then we don't have to haul our vehicles all over the place. So we have a roadmap for that service, and it's already in a mobile version. Maybe someday we'll make it available as an app. We'll see. But I mean, to be honest with you, the cameras and phones are absolutely state of the art these days, and in many cases are superior to the cameras in your cars, because those are probably, even if you have a new car, they're probably still sourced 5 years ago. So anyway,
you literally have a roadmap.
Yeah. Yeah.
That is the challenge with onboard vehicle technology, right? Most of us buy a vehicle and keep it for 12 to 14 years, or even if we don't, somebody does. Most of that technology isn't easily replaceable. People replace their phones every year and get new technology on those, but the car is sort of stuck with what was being put on it when it was engineered 3 years before it came off the assembly line. So that's an interesting comment that we always probably need to sort of keep in mind as we look at these features. Now, of course, cars now have software upgrades which improve the processing features that come from some of these technologies.
And let's stay on this question on data for a little bit. So Peter, it sounds like you've had a lot of hands-on experience in kind of getting the package data from Phil and using it. Has UDOT ever seen a need to access the raw data? And then Phil, I want to ask you to elaborate a little bit more on a point you made during your presentation on translating this data into actionable information. So Peter, do you feel like kind of what you've been getting really helps to meet UDOT's needs? Have you ever had a need to kind of dive deeper into that raw data?
I haven't looked at the raw data at all. I've used the portal and have looked at segments there, analyzed some of the features called out in the report. You can look at that, but as far as raw data numbers, no, that hasn't been a need yet. So.
Well, and the raw data that's why we host it on a server. I mean, it's terabytes of data. You wouldn't even it would take you 2 days to download it. So you can download the portal. You can download 200 frames at a time into a GIF or an MP4. And so the thinking there was that, okay, well, we'll take one of these items, a call out that's important. We want to forward it to somebody. So at least you have a file that's a little bit more manageable. Yeah.
That sounds like a great feature. Not only are you processing the data, but you're packaging that up in a way that, UDOT was able to kind of use more seamlessly.
Yeah. And an interesting comment I'll add there. When we originally contracted with VSI, they didn't have that portal. And so we had this question about how are we going to get, they're contracted to provide us a written report. And so that's what caused us to have this discussion about data and how should we get it? And should I mail you a 4 terabyte hard drive and have you download to it and all this? And he said, oh, we're developing this portal. And by the time our data was processed, they had started to develop that portal. We provided some input to that, and they've continued to expand the portal. So like with many things we do, everything's a work in progress. Everything is evolving and expanding as we go. And we're able to kind of play a role sometimes in helping to craft how the evolution occurs.
Mm-hmm. Blaine, I love that point. Were there other things during this deployment where you guys innovated on the spot, where you said going into it, maybe you didn't realize you had that need, but as you were in the thick of things, you saw that, if you did things a certain way, you'd have a better outcome?
Well, I would say one of the biggest challenges we had was it was the first survey. It was hot, it was well in the 90s, and all of our computer gear in the trunk, recording all this data. There were a couple times where we literally had to pull off the road and let the computers cool down. So that was a little bit of a challenge, but those are just challenges. We're now better with our thermal management, so we found solutions to that. So yeah, that was an on the spot thing. Bugs, on the sensors, these things just happen. You kind of run into edge cases of your own, when you're doing something like this. A flat tire, for example, things like that. It's I can say this, the scenery was real good though.
The thing that comes to my mind, and this isn't really an on the spot kind of thing, but we anticipated doing the first phase and gathering I-15 and 89 and Big Cottonwood, and then seeing how well it worked before we decided to do a second phase. And as we were showing the results to some of the other folks here at UDOT, they started to say to us, well, have you done this in the rain? Have you done this at night? I'd be interested in seeing that. So when we did the second phase, we had to get a little creative, but we had them do I-70, a piece of it in the daytime and a piece of it at night. We hadn't anticipated that in the original contract, but we were able to shuffle some things around to make that happen. And it was just sort of feedback from ultimate users here in the department who allowed us to think about that, and then execute that to get another set of data. And as Phil showed, there's a difference daytime versus nighttime. And then as he described, there's a difference in a snowstorm. So yeah, there were a few things along the way like that.
Yeah, that's really helpful. I think you mentioned in your opening remarks that we haven't yet invented the technology to dictate to Mother Nature when it should rain and when it shouldn't.
Yeah, that's right. We're working on that, but yeah.
Another offering that VSI Labs does. Well, let's pivot a little bit. We've had several questions about the actual devices, like the cameras. You guys have probably
Yep.
seen this in the chat. So let's talk a little bit more about those sensors and cameras. We have a question from Radha. Is the car shown on Phil slides a level 4 or 5 automated vehicle? Or is this a regular car with lidar, sensors, and cameras?
It's a great question. Yeah, that vehicle is whatever you want it to be. That's a by-wire development vehicle. We can program that. If you know, level 5's not practical. Obviously, there's just too many limitations that are going to prevent that from happening anytime soon. We could outfit our car to operate as a robotaxi, as long as we outfitted it with all of those sensors. And so now for that type of use case, instead of a $500 or $1,000 ADAS package, now you're talking about $150,000 sensor package that would enable, you know, that level of automation. And to answer the question, yeah, we could do all of that, but we're not really out to prove anything ourselves. We're testing the individual sensors on individual applications, because if those break down, then you're never going to make it to 3 or 4. So
I'll sort of weigh in on a different angle of that question. Although the sensors on the vehicle could possibly enable full self-driving level 4 kind of operations, these were, as I recall, Ford Fusions.
Yep.
that Phil's team had retrofitted with this technology, and they were being driven by a human at all times. So at no time were these vehicles driving themselves. They were level 0 vehicles, I suppose, with a whole suite of sensors gathering data. It was just a regular car with a bunch of sensors.
Yeah.
It was a simulation, essentially.
Yeah, and a bunch of computers to record that data.
And so again, there comes some of the evolution. As I indicated, our first step into this project was to see if we could find a vehicle that could drive 300 miles through our state without human intervention. And the vehicles that they brought in might have been able to be retrofitted to do that, but we decided along the way that wasn't really the practical thing we needed to do. The practical thing we needed to do was to assess our roadways. And so we pivoted away from that original goal. And these vehicles drove themselves. These vehicles were driven by humans.
And to that point, just based on my own experience, I doubt there's a level 2 or 2+ system out there that could go traverse a state entirely without a disengagement. You'd have to be pretty lucky for that to happen, and you'd have to plan your route in such a way to avoid exposure to vulnerable scenarios. So that in itself would be a challenge. So yeah, our goal was to take a look at, let's see how well the cars read the road, and find out what problems, because let's start with that and address those problems, because that takes care of the current market and all these ADAS technologies that are coming in. 60 to 70% of the cameras. And I will add too, the NHTSA, the recent NHTSA activities as it relates to pedestrian detection, their next domain is lateral control, because lane departure accidents, I believe, are the highest cause of fatalities on the road. And so they're going to prioritize that after they get done with this round. And so, yeah, there's going to be all kinds of new requirements for both the infrastructure as well as for the automakers.
Well, and you make this point about reading the road, Phil. We have a question from Yashitla. She asks, does the AV vehicles, do they read the speed limit? What happens when, it reads a road marker like US 301? She mentioned she's got a 2023 model car, which is capable of adaptive cruise, but it reads like a sign that says US 301 and tells the car that it's a speed limit 301. Have we seen that as a challenge?
There's a couple ways you can address that. And you can do it through a speeds. Well, first of all, if it's in the map, if it's in the map of the vehicle, you know, the vehicle's going to have a map, at least for getting from point A to B, that's going to have a associated posted speed limit. So, that's one way to control the top speed. But most of these systems allow you to set the top speed at 5 or 10 miles an hour above the posted speed. That's just the way they do it. And now in Europe, there's new regulation called intelligent speed assist. So every car sold in Europe now has to have the ability to know the posted speed in the area it's at and not to exceed that. So, and that's likely coming to America too.
And Phil, is that being done with the camera on board, or is it all map based?
It can be either. You can do it with a camera. It depends on how you want to implement it. They allow you to do it with a camera to read the signs, or if you have an ISA certified map, then you can cover it that way.
Well, and speaking of maps, so Sushanta asks about geofencing. If an automated vehicle is operated in a geofenced area, like scanned and mapped prior to the deployment, will lane marking still play a role in that automated vehicle's operations?
What was the first part of that question again? Sorry.
So if the AV is in a geofence, do you really even need to use lane markings to help?
Okay, geofencing, the application is going to restrict its operating domain to within an area. It could restrict it to a geographic area. It could restrict it to a road type. But that's generally how the industry applies that terminology within the context of operational design domain, where it can and can't be used. But the answer to the question is no. You have to have, that vehicle has to have a way to localize, okay? And choice number one is through what it sees. And that's going to be markings. Again, if it's a higher end implementation, you might have a lane model in the vehicle that's going to give you, but if that's the case, then you need a high performance positioning device to operate within that model. So that's a step up in terms of capability.
And the GPS capability on today's vehicles isn't that precise.
It is not. If you're operating with a lane model and you want to have that ability to stay in the lanes, even if you can't see anything, you would need a high performance GNSS device, like with RTK or some sort of RTK system or RTX or like a Trimble type solution.
Kind of
so
to your earlier point that even a new car has outdated technology sometimes, right? Because once you get it off the manufacturer floor, whatever those devices within a new car are probably at least a few years old.
Oh, most likely, yeah, or most always, yeah, frankly. Now here's the beauty of some of the new, you've probably heard, the software defined vehicle and over the air updates. This is all part of the kind of the new architecture for vehicles. And what that means is that as a software defined vehicle, you can apply, you can download or automatically flash the algorithms in those vehicles to introduce new performance capabilities, even new features. I mean, if anybody has a Tesla, they know with these updates, I mean, the HMI even looks different after a couple of years. There's new features, there's new applications. And so this is a way to keep the technology current. And this is a huge trend, is how does the industry transition to that type of model? And the software is really the key to keeping the technology relevant to a point.
Okay. Moving on just a little bit. So we had a question from an anonymous attendee about pavement conditions. I know we've been talking a lot about lane markings. Specific to the deployment, did we pick up any pavement conditions and analyze that? Blaine, I know that UDOT separately utilizes lidar for assessing pavement conditions on our transportation system. So was that part of this deployment, or is that kind of a separate effort?
Yeah, that wasn't our intent here. Our intent was really to look at whether our infrastructure supports ADAS features. We have had other projects where we have attempted to or proposed to look at pavement conditions in real time. And there are some commercial products out there that do that. Frankly, as we started looking at that, our maintenance engineers told us that they don't really need that information in real time, that they have good sources for that information on their periodic surveys, and their response to those issues is really gauged upon that. And so we've sort of backed away from trying to do real-time pavement analysis. Now, other agencies may have a lot of interest in that, but that's something we've backed away from. We do every other year a complete lidar scan of all of our state highways, and that informs our asset management process and looks at things like conditions of guardrail and signage. And it's a very robust system that our department uses completely, but this particular project wasn't focused there.
And speaking of pavement conditions, Matt asks if we picked up rumble strips. Was that part of it?
Well, we did, and we found that actually interesting results. We saw it on in a couple of places. I think it was on 50, maybe 89 too, where we see it down the center line, and then the striping is right on top of that, so the paint's applied right to that. And so the combination of those two things actually improved the performance of the detector. And as I said before, if that lane is solid, it's going to work well if that rumble strip is there or not. But if it begins to fade a little bit over time, that rumble strip will, in my opinion, will extend the longevity or the machine readability of that. And if you took away lines altogether, the painted surfaces, and if you just had rumble strips, I'm sure the vehicle would do just fine, because it would detect those, again, if the algorithm is trained for it, and would be able to maintain full lateral control.
But it was interesting, Phil, in the one video you showed today, it picked up the lane stripe, which was on top of the rumble strips in the center line, very well. It picked up a lane stripe on the right side, and beyond that lane was a rumble strip, and it didn't seem to confuse it. It seemed to know the difference between the pavement marking and the rumble strip, and I didn't ever see the right-hand line jump over to the rumble strip. So I don't know if that's just part of the training in the system.
Yeah, exactly. It's going to prioritize its longitudinal marker that's giving it the best return. And so at that, right in that area, that painted, like I said before, if you have some scars, you can overcome problems with that. If your main markings are solid, it's going to take priority. And so that's what's going on.
Okay. Well, I'm going to just ask a question from John Olson that builds on, I think, what you're saying here, just in terms of how to, use this type of technology going forward. He asks, are there any thoughts about modifying standards, such as increasing the width of the stripes or encoding stripes in some way to differentiate, like an exit lane, a center lane, something like that?
So there is a lot of discussion today about modifying standards, and FHWA is about to issue a new version of the MUTCD. Many states, including ours, have gone to 6-inch stripes on the interstates, or at least on key interstates, instead of 4-inch stripes. What we found in this particular study, though, was that it wasn't so much the paint width as it was the marking quality and contrast. And so, Phil showed a couple of examples where the exit lanes aren't separately marked. I think the new MUTCD shows, I don't know if it's optional or required, a short dash, a dotted marking, if you will, across turn lanes to sort of solve some of the problems that Phil talked about. And so I think there is an effort to incorporate some of those kinds of things into our standards and standard practices so that we can mark those better. Frankly, those are better for human drivers as well. I think a lot of the reason agencies are going to 6-inch stripes is those are better for human drivers. But some of the primary modifications that this study sort of points out, in addition to simply having good stripes, is the tiger tail stripe, for instance, on concrete pavements, where instead of putting white on gray, you've got alternating white and black stripes on gray. We found that those work really well and really enhance the ability of the system to pick up paint stripes. So there are some of those changes in the works, at least as options, and the standards groups are considering those kinds of modifications.
I just make a note that a follow-up comment from Eva Lerner-Lamb. She says, it seems that the results of this kind of research, codes and standards for state DOTs and the federal DOT for lane marking, et cetera, might make sense.
Yeah. And you know, the codes and standards are a slow moving process. I'm involved in some SAE standards right now, and it's a multi-year process to consider and gain consensus. And we just saw the MUTCD go through that kind of a process over about a 5-year period, where they looked at some of these pavement marking issues and looked at studies and looked at efforts that were involved there. The AASHTO has also provided a transportation operations manual recently that has a chapter on connected vehicles and automated vehicles, and some of these comments are in there. It's sort of an evolving practice, but it behooves us to absolutely consider these kinds of results as transportation and vehicles change, to make sure we're moving forward appropriately to support these kinds of technologies.
Bill, do you have anything to add there? I think you serve on a few national committees as well.
You're right. Yeah, no, it's MUTCD, for example. Yeah, that's the Bible for this type of thing. And it is I think it might still be recommended, those dashed markers on those ramps, but the addressing machine vision systems is increasingly becoming baked into to those standards. But on a related note, you know, you have retroreflectivity. Of course, that's a standard that's pretty important. And we recently did a survey in Texas, and we did it alongside a retroreflectivity machine. So we haven't correlated it yet, but that's the goal, to correlate and see if we're seeing a strong correlation, because we don't measure retroreflectivity. We measure the performance of the computer, and we get KPIs and confidence values and things like that, but that's a different metric. But we can assume that there is a strong association between those two.
I'm going to pivot a little bit. We have a couple questions associated with specific geographic areas. So Ben Williams asks if we're considering a future deployment of this kind in an urbanized area. It looks like what we've done so far is primarily located in Utah's rural areas. And then the second question is from Mark Perry, and he asks if we tried this technology in a work zone. I'm going to kick it to anyone who wants to answer those.
Because Utah is a big state and our roads are long, a lot of them are in urban or in rural areas. But we are a very urbanized state in that about 3 million of our 3.5 million people live along what we call the Wasatch Front, a narrow 70-mile stretch of of land along the base of the Rocky Mountains here in the Salt Lake and Provo areas. This survey did include freeways in those areas. I-15, a piece of I-80 were in that urbanized area. And some of the results that Phil showed and are in the report talk about the capability of this system in urban areas. And so that was part of the study. And it was just as effective there as long as the pavement markings were adequate. So that it worked just as well there as it did in the rural stretches. The second question was, remind me.
Zones.
Work zones. Phil, do you remember? I'm sure there were work zones you passed through.
Yeah, we had several work zones, and although I don't condone the use of automated technologies in a work zone, if those work zones are well marked, the system can read those temporary markings just fine. And we had several examples where it was able to read the road well in those work zones because they were properly marked. We had a couple areas where there was just too much going on, like on I-80, for example, within the 215 loop, a lot, especially toward the Wasatch area, it was a lot of construction in there, and there was just so much going on. There's some patchy surfaces, there were lane scars, there was just so much going on that it failed in some of those areas. But some of the ones on the interstate were reasonably well done. Even though I don't recommend you should always disengage that stuff when you're coming into a work zone. In the future, we'll be able to
in the
automate.
future, we'll get to the point where you've got level 4 and level 5 vehicles, and they will necessarily need to pass through work zones. We need to figure out a better way to mark those. The follow-on is also true. You noticed in some of the videos that Phil showed, we were driving over former work zones where some of the temporary pavement markings hadn't been adequately obliterated, and some of the permanent pavement markings hadn't been put there yet, and we still just had fresh asphalt, right? So those are all problems. Those are all challenges that we've got to figure out how to be better at as these technologies become more prevalent.
I think it comes down to your work zone standards. You need to have efficient unmarking, like you mentioned, obliterating the old pavement markings. Some of the slides, some of the images I've looked at, you see where it picks up the correct pavement markings and avoids the blacked out markings, or other times, the ghost markings throw it off. But it comes down to, study like this can help you improve your work zone standards to say, we really need a good removal as well to clarify the new markings.
Yeah.
Okay. Yeah, I certainly wouldn't want to be a construction worker in a work zone with a lot of self-driving cars flying by me. Not yet. I have a couple of questions about the software and sensors that have come up since we talked about it earlier. So one question comes from an anonymous attendee. How does the system based on open source software used in the study compare performance-wise with LKA systems provided by OEMs already?
Very good question. The problem with everybody's LKA system is it's a black box. Okay, and that's a problem with AI systems in general. So you really have no idea what is causing it to do what it's supposed to do or what it's not supposed to do. So it's extremely difficult to try and decompose an OEM solution other than a side-by-side comparison, and that's what we did. And our benchmark vehicle is a Tesla with Autopilot 2.0, and so we regard that as state of the art. And all these issues that we identified in the study are ones that would cause problems with the Tesla as well. We didn't benchmark the Utah one. We didn't bring an extra car out for that, but we've done quite a bit of that locally to correlate the two. And we think our detectors are as good, if not potentially better, overall. I mean, at the end of the day, we're looking for analytics. Okay, better data is going to be better analytics. A lot of the LKA systems out there, and remember, as Peter said, an LKA system is going to they'll find the line, and it's going to want to nudge the vehicle back rather than maintain full centering. It's sort of a little safety net. And the performance of those LKA systems is really not very good, because often it just can't correct, or doesn't see the marking very well. But it's really the latest generation of lane centering assist, which is available in pretty much every OEM's lineup now, is going to have state-of-the-art performance as well.
Okay. Perfect. You mentioned artificial intelligence, and I'm going to take the facilitator prerogative. No one that's joining us here today asked this specifically, but I have a burning question. Artificial intelligence is a hot topic these days. We're seeing it really just explode on the scene in every aspect and facet of our lives. So with automated vehicle technology really kind of being an earlier adopter in the utilization of AI, what do you all think are some of the pitfalls or challenges that we'll need to mitigate going forward in using AI in future deployments? And then what are those opportunities we really should leverage, because us humans can't do it all? Let's start with Blaine, then Peter and Phil.
So a couple of things come to my mind here. And the first one is something that Phil mentioned. So maybe I'll steal his answer. Hopefully he has another one. These systems are built on video analytics. And we have a lot of systems in our lives today that are built on video analytics, security cameras in the airports and just all kinds of features. Our phone, frankly, uses analytics on the video or the still images that it creates and can tell you where you are, those kinds of things. AI has a huge potential to improve the capability of recognition of images in still or video photographs, if you will, right? And so the key there then, my second point, what we need to do moving forward, these all need to be trained. Artificial intelligence is really just a process where the computer looks at everything it knows and tries to extrapolate beyond that. And so we try to train the computer with more examples of what images look like. I think one of the challenges with automated vehicles today are that they can't identify everything they see. And so therefore, some of the situations they find themselves in, some of the edge cases they're in, are because they don't really know what everything around them is. Artificial intelligence will help us to solve that problem. And you're right, Muriel, we're seeing AI, we're talking about AI in every aspect of what we do. Video analytics, I think, is a great case. The other piece I'll throw in, Phil mentioned that we've got terabytes of data. In our connected vehicle work, we have terabytes of data. AI will help us start to sort through that data and find trends and useful information there. That's how I see it.
That's fantastic. That's, as a non-subject matter expert, to better understand how AI can help improve my life and improve the safety of our roadway system is really helpful.
Phil may have some additional, yeah.
Yeah, we're not, obviously we're not using generative AI for reading the road. And so that's really kind of a different animal. In the case of these applications, you're using AI for a very specific thing, and that is to be able to detect and classify with confidence that there is something there. Okay. And as Blaine said, it's all about the training of those detectors, and you feed it with massive amounts of images and samples that have known ground truth. So it's labeled data. So you're supplying all this input with all this associated output, and then you build your model, and that's part of the inference builds the inference model. And then, that's the starting point right there. And then as time goes on, you collect new data, and then you're able to retrain that network to become, better at, detecting whatever it is you're trying to detect. So it's not used in a bad way. I would say in automotive, however, and this is functional safety, back in the day, not that long ago, artificial intelligence would not pass functional safety standards because you cannot do a proper analysis of what the neural network is doing. And it's a probabilistic outcome. And but now there's different metrics and different ways to assure that the system is certified to meet certain levels of performance, really from an outcome standpoint. So AI and automotive haven't always gotten along, but now when it comes to now, everything's different now, and AI is being adopted in many ways.
Fantastic. What do you think, Peter?
Yeah, and there's going to be more to learn. I mean, you can feed every possible scenario you think into the AI today, and then tomorrow something new will show up on the roadway, whether it's a maintenance project or a utility line come and dig up the pavement, so it looks different than the last time I looked at it. Or there's a new type of vehicle on the road. You can't feed every image of every vehicle, and then somebody shows up on a recumbent bike and it's never seen that before, or a scooter. Or so yeah, we're feeding it massive amounts of information. We're doing these road surveys, but there's always something new to it to learn. And so yeah, that's AI. It learns from all this massive amount of information, but right now we still have a human in the loop, right? Because it finds a situation it doesn't know what to do with, and it stops, or yeah, is to interrupt the flow of it.
Well, that's why all these systems require a human is still in the loop. Okay,
Right.
they have the final call, and so that's why the driver monitoring systems to make sure they're watching the road. Some cases you require to hold the wheel, even though it is full lateral control. It wants to make sure that you're still engaged. Because it's not a question of if, it's just a question of when that vehicle is going to get in a situation it's not going to know what to do, and it's going to call for an immediate takeover.
And so whether the person's behind the wheel or remotely, some of these driverless robo-taxis, they still have a remote monitor going on too, so they can take over or come on the intercom and say, hey, what's going on? Your vehicle stopped.
Well, the Tesla vehicles were being cited for so many collisions with emergency vehicles.
Right.
And it's just because their algorithms were not trained to identify those vehicles. At least that's what they say. But there's a lot of scenarios where these robo-taxis are getting jammed in certain areas, and it's a lot of it's got to do with emergency vehicles. You heard about all the stuff in California and all the the controversy over the potential disruptions that these fleets of robo-taxis can encounter, or even create when they approach a situation that's got a lot of emergency vehicles.
Well, and that actually gets to, I'm going to ask two more attendee questions, and then we'll ask for your parting thoughts. So Brian Romansky asks about the role of V2X technology in supporting autonomous driving. I don't know if, kind of your point about, emergency vehicles and kind of, signal priority perhaps at signalized intersections, plays a role in these challenges. How will autonomous vehicle technology sync with the V2X systems that UDOT is setting up?
So I think that's a great question. And I believe there's a fairly broad range of opinion about that. I know that some of the automated vehicle developers feel that they can't rely on V2X data, and so therefore they're not going to use it. They would like it if they could get it all the time, but they don't feel like they can. I personally believe that V2X has a huge role in making automated vehicles more successful. There are edge cases that we've talked about where the automated vehicle may not be trained to recognize certain things, and information being sent to the car through a V2X transmission can help that. even beyond that, I look at an automated vehicle as a vehicle that operates based on what it can see. The sensors on board the vehicle are seeing things around it, and the automated vehicle responds to those. It can't see what it can't see, right? So the beauty of V2X is that we can tell the vehicle things that it can't see and allow it to operate itself based on what it can learn about the environment around it. A couple of classic examples. If your vehicle is following another vehicle, it can't see the vehicle in front of that one, which when it puts on its brakes, you won't know until the vehicle immediately in front of you puts on its brakes and the sensors in your vehicle respond to that. V2X could tell you that. Secondly, the automated vehicle can see the traffic signal and know whether the light is red, yellow, or green. It doesn't know when it's going to change, but V2X can tell you that. V2X can tell you whether someone's going to run that red light in another direction. So there's all kinds of value. And I know there are some automakers who believe in that redundancy and that symbiosis between automated vehicle sensors and connected vehicle information. And I subscribe to that. I think there's a huge role there. But you know, the automated vehicles are being developed by vehicle manufacturers, and they control what goes into their cars. They don't control what we put on the roadside. So on the roadside, we need to step up and deploy connected vehicle technology and demonstrate to the developers of all sorts of vehicles, automated and not, that we have information to share, that we're willing to share, and that we're willing to help them with that. So I think there's a huge role, but I think we as agencies need to step up and demonstrate that it can be done.
Yeah, I fully concur. Yeah, I mean, and especially in urban environments, you need that more than ever. When that automated vehicle is out in rural areas, it's going to rely more. You're not going to have connectivity in all those places,
Right.
And so you have to have the intelligence on board. But there's a reason there's a C in CAV. The connectivity and connected services in general is a vital part of the equation, and for all those use cases that Blaine mentioned, and I couldn't agree more. So yeah.
So vehicles will be autonomous, but they need to be syncing and talking and connected with the system they're driving on.
Yeah, particularly with these dynamic events that happened, when something, falls onto the road and creates a blockage, and it's instantaneous, you need to aggregate that content immediately and be able to distribute that to the oncoming vehicles. And there are companies working on that. This is kind of like Waze. In a sense, it's telling you there's a disabled vehicle order, but just think of that, this crowdsourcing in the future, being able to aggregate those dynamic events in real time, and then be able to redistribute those safety messages to the oncoming vehicles to avert, potential problems.
Mm-hmm. Okay. Well, with that, I would ask for each one of you to take 30 seconds up to a minute and provide our attendees with your parting thoughts. What is the biggest key takeaway that you hope that the hundreds of people that joined us today will learn from our webinar? Let's go, Blaine, Peter, and Phil.
So two things really quickly. First of all, there are things that we as agencies can do to help support the evolution and development of automated vehicles. And we need to step up and do that. And one of those things is our lane markings. Secondly, we learn from doing. And so as agencies, we need to step up and do some of these things, try them out, not be afraid to maybe do something wrong or to fail, and to just do it and move forward. There's a huge amount of learning involved in the kinds of things that we're trying to do here.
Yeah, I would say lane markings matter more than ever, not just for human drivers to see them on the road, but the future automated vehicles will use them too. So they have to be clear And whether they're temporary or permanent, yeah, they have to be clear and readable. So maintenance matters. Phil?
Yes, I used to, in theory, you could operate without markings. I mean, if every vehicle had all the technology and had these virtual high definition maps, so your virtual markings are in the computer and it's positioning itself. And if everybody was on the grid, you could, in theory, do it without markings. That's not happening anytime soon. Okay. At the end of the day, the markings are the ultimate ground truth, like I said, because you're gonna prioritize vision systems above everything else. And and like I said before, what works well for the machine works well for the human. And as I also said, if the human can't see very well in a certain condition, there's a pretty good chance the computer can't see it either. So
So if we learn anything else today, it's lane markings, lane markings, lane markings.
yeah. Really,
Okay,
yeah.
well, thank you so much. We are right at the top of the hour. We appreciate all of you who have joined us today. And thank you, of course, to our presenters. I personally have learned a lot, and I hope everyone else has as well. We will be sending follow-up materials, including the webinar recording, via email in our post-webinar correspondence. And all of this information will be made available within 1 week on the UDOT Transportation Technologies website. Thank you again for your participation, and we'll be in touch.
Thanks, everybody.
All right, thank you.
Thank you.